Alright, hello, I'm Zachary. I'm a tutor for Chegg, and today we're going to talk about volumes of revolution and how to find those volumes using the washer method. Now, many of you may already know this, but a washer looks like a disc, alright, with a smaller circle punched out of it. Let me get this circle, move it into place. Alright, so the area we're interested in is this one right here, the area between these two circles. Okay. Now, if the inside circle has radius little r, and the outside circle so I'm just choosing letters to label things I don't know, then what's the area of the washer? Well, the area is equal to pi times r squared, that's the area of the big circle, minus pi times little r squared. That's the area of the little circle that we punched out. Okay? And this is the area of the smaller one. Okay? So, if we have a shape, and if we can cut cross-sections perpendicular to an axis and get washers, then we can use this formula for the area of the washers to integrate, to add all those cross-sections up in order to find the volume of this area that we have revolved around one of the axes. So the equations in those cases look something like the integral from a to b of pi, and I'm going to factor out the pi here just to make life easier, pi capital R squared minus little r squared dx, or it could be dy. We'll do an example of both. Alright, so this is the idea. This is the outer radius right here, the capital R, and this is the inner radius, the little r. Alright, so here I've got an example planned, and so the area we're interested in is right here, between y equals x and y equals the square root of x, and we're going to rotate it around the x-axis, alright? And then if we cut that, if we take cross-sections perpendicular to the x-axis, what do we get? Well, there we go. We get discs that look like this. Let me change that color back. There we go. Except there's also a small hole in the middle of them. Alright? So, the question is, well, let's get started then. Let's set up our integral. We're making cuts perpendicular to the x-axis. The x-axis is right here. That means that we have to integrate with respect to dx. So we'll integrate, and we'll have our dx over here. Now we gotta wonder, what are our limits of integration? Well, they're going to go from where we start taking cross-sections, which is right here at x equals 0, to where we stop, which is right where these two curves meet. And at that point, if you set these two equations equal to each other and solve, you'll find that that occurs at x equals 1. Alright? So now we have pi, and now we have to figure out the inner radius and the outer radius, and we're going to square it, and then we're going to subtract off the square of the inner radius. So here, the outer radius is given by the square root function. The outer radius is, I don't want that black. The outer radius is right here. I drew it slightly away from the blue circle so that you could see it better, but I hope you can tell that this outer radius right here goes from the x-axis all the way up to this square root function. So the outer radius has to be the square root of x. And we have to square that radius. What about the inner radius? Well, the inner radius is given by the smaller function, the function closer to the x-axis. And this is the inner radius right here. Okay. So what do we have there? We have x. We have x squared. Okay, now we're just going to solve this integral. So we integrate from 0 to 1. Pi, the square root of x squared, that's just x, minus x squared dx. Parentheses there. And let's draw that a little neater. Need a parentheses. Okay, now if you solve this, you end up with pi times 1/2 x squared minus 1/3 x cubed. And what points are we plugging in? What x values are we plugging in? We're plugging in 0 and 1. If you do that, what you find out is that pi, the volume is pi times 1/6, or 1/6 pi. Alright? Let's take the same area here, the same figure in the xy plane, and let's rotate it instead around the y-axis. And let's see what happens. How does it change the integral? How does it change the result? You might think that the volume would be the same, but that's not true. Alright, and we're going to prove that. So here's the area we're looking at again, right in here, between these two curves. Alright, so if we slice it with respect to the y-axis, we end up with discs, we end up with washers, these discs with holes punched out of them. Okay? That drawing isn't perfect, but you can get the idea. So we want to integrate with respect to dy, because our cross sections are perpendicular to the y-axis. We want to integrate from where these cross sections start. They start at y equals 0 and they go all the way up to y equals 1. And then we're going to have our pi, and then we have to decide on our inside radius and our outside radius. Okay? Our outside radius goes all the way from the y-axis to this line, to y equals x. And we need it in terms of y, so we're going to use this left-hand side of the equation, y equals x here. And that's going to be our outside radius squared. What about our inside radius? Well, the inside radius, the black disk, goes to this square root function right here. Right? So the inside radius is given by the x value of this point. Well, we have the equation in terms of it's solved for y. We need to solve it for x, so we have to square both sides. And that gives us y squared equals x. If we take that and we put it in here, well, y squared is going to give us our inside radius. Alright? But we need to square it again, because we want to take the inside radius, which is y squared, and then square it, just like it tells us in this formula here. Okay? And now we just need to work that out. So we integrate from 0 to 1 of pi times y squared minus y to the 4th dy. That gives us pi times 1/3 y cubed minus 1/5 y to the 5th, and we're plugging in the values 0 and 1. So then we have pi times 1/3 minus 1/5 after we plug in these two values here. And I don't want that as a bracket, I want that as a parentheses. There we go. And so then we'll subtract one of these fractions from the other, and we'll get 2/15 pi. Okay? So here we got pi over 6, or 1/6 pi. And here we got 2/15 pi. I need to write a pi here. There we go. 2/15 pi. And so what this tells us is that two shapes that you think might have the same area don't necessarily have the same area. You have to use the math to make sure that your intuition is correct. All right? I hope that helped out, and that's the end of that lesson.